case of a stone tied to a string and revolved in a vertical circle. This is stone, this is string centered at O, and this is moved in a vertical circle. So obviously this motion is a non-uniform circular motion. Now it is asked, that is, what is a minimum velocity it should be having at the top so as to that it is able to navigate the circle. We can easily understand, if the speed is good enough, is high enough, it will easily continue to move in the circle. Then there is going to be one speed where it will just complete a circle, and if we go below that, so probably it will come over here and it fall like this. So this will not navigate the complete circle. The maximum danger or maximum risk for this stone to fall down, to deviate from the circle, is obviously, if it is able to navigate the top, then it is safely, it can complete the whole circle. Let's say at this point A, it has any arbitrary value of speed as v. If the speed of velocity over here is v, then certainly we know that a centripetal force is going to be mv square upon r, where r is the radius of this circle. So F centripetal is mv square upon r. This is the requirement. If it is over here, the speed is v, then certainly it requires a net force towards center whose value should be mv square upon r. Then we look for the real forces which can contribute to meet the requirement. Over here, if we draw the free body diagram, one is tension is all away from the body, and the second is mg is also acting in this direction. So there are two forces. So T plus mg in combination, they meet the requirement, mv square upon r. Obviously in a string, when pull it, we can keep on increasing tension. At one value, the string will break. Similar over here, the tension somehow also adjusts itself to certain limits. Let's say the speed is very high and the requirement for this mv square upon r is suppose 200 Newton. And let's say the value of mg is 100 Newton. So the tension will adjust itself to 100 Newton. 100 plus 100 is equal to 200. Now we have reduced the speed over here at the topmost point. In the next circle, suppose we have reduced the speed. And now as the speed reduces, m is same, r is same, let's say it drops down to 150 Newton. mg is a non-varying force, this is fixed, so this is 100 Newton. So now the tension over here in the string will adjust itself, it will become more relaxed now as compared to a previous case. So it will come out to 50 Newton. Speed is still lowered, it comes out to 100 Newton. So 100 Newton is met by this mg 100 Newton only. So as a result, this string is totally relaxed. There is no tension in the string. Now, if we drop it further, let's say over here, the requirement velocity speed is further reduced and comes down 90 Newton. But mg say that is, I can't go below this thing, my value is fixed, it is 100 Newton. 100 Newton. So obviously the circle will not be completed. This will deviate further from the circle. So this is the worst case or best case when the circle can be navigated. So it means when it just navigates a circle, that is, it is at that minimum velocity, we are talking about that minimum velocity when we talk about, then T plus mg is equal to mv square upon r, and T should become equal to 0. In able to navigate the circle, the most critical point is the topmost point. Once it is able to navigate this topmost point, it is able to complete the whole circle. If it just navigates this circle, then the tension in the string when it is at the topmost position, that should be equal to 0. That is, the whole centripetal force is being provided by the weight of the body. That is, we say mg meets the requirement, mv square upon r. So v is equal to under root rg. So v is equal to under root rg is the minimum velocity for a body to move in a vertical circle of radius r, and this minimum velocity is only for the topmost point. It is not for this point, this point, this point, any other point. It is only that this should be velocity at the topmost point of this stone which is tied to a string and being revolved in a vertical circle of radius r. Then its velocity, if it is under root rg, then it is going to navigate the vertical circle. If it is more than that, still it will navigate the circle unless until the string breaks. And if it is below it, under root rg, then it is not going to navigate this circle. This is the case of a stone which is tied to a string. The other case, similar case could be, let's say there is speed breaker, there is a hump, and this is radius r, and there is a car which is going like this. This is over here, this is circle of radius r only, We know if the speed is high, at any point this car can lose contact with this circle. We know similarly over here, equations they are going to be, mg is going to be in this direction, normal reaction onto the body is in this direction. Suppose speed is v, so requirement is mv square upon r, and this is going to be met by mg minus n is equal to mv square upon r. Mv square upon r is the requirement of centripetal force toward the center, and along the radius there are only two forces. One is mg, which is acting on the body in the downward direction, and n is the normal reaction which this surface is applying on the body at angle of 90 degree. So along this radius there are two forces, one is mg, the other is n. Net force is towards center, so that's why mg minus n is equal to mv square upon r. If this car is moving slowly, then certainly there is going to be some normal reaction. But as the speed is increased, the contact force between car and this surface will be reducing. At one value, it will happen, that is if the velocity reaches that value, so that n almost becomes equal to 0. That is, it just loses contact with the surface or is just in contact with the surface, then n becomes equal to 0. When n becomes equal to 0, that is mg is equal to mv square upon r, or v is equal to once again equal to root rg. So over here in this case, this velocity is the maximum velocity so that this car stays in touch with the ground. If the velocity of the car goes beyond this velocity, then it will lose contact with the surface. So when we say V minimum is root rg, we mean that is this is the velocity, that is this stone must be having, it must possess this velocity, it must be having that velocity at the topmost position to navigate this circle. But it can also be asked, what is the minimum velocity, should be over here or should be over here, so that it is able to navigate the circle. In all these cases, it is being indirectly asked, that is what is the velocity over here. What's the velocity we give? If it is minimum velocity at the lowermost position we had given, then it means when it goes from here to here, the potential energy will be increasing, kinetic energy will be reducing, and the velocity will obviously reducing, so that velocity gets reduced, and it should get reduced in such a manner so that when it comes over here, it possesses root rg velocity. It has a velocity root rg. Let's find the velocities the same stone, the same body should be having at the points C and D, so that it is able to navigate the circle. This can be found easily by using the principle of conservation of mechanical energy, which we have done earlier. It means that is mechanical energy at, let's say we take the two cases A and C. Mechanical energy at A is equal to total mechanical energy at C. Mechanical energy at A is mgh, potential energy. Potential energy what? Mg, this is R, and this is the reference level. So mgh, mg2r plus half mv square, kinetic energy. V is root rg, so square comes out to be rg. So this is potential energy of this body over here. Reference level is this, r plus r, h is 2r, mgh plus half m v square. V over here is root rg. We have taken root rg because once we are asked what is the velocity should be over here, that is this is a minimum velocity it has been asked. So it means when it is going up, the velocity over here should be root rg. If it is more than that, then certainly we cannot call this as minimum velocity. So potential energy plus kinetic energy over here is equal to potential energy plus kinetic energy over here is equal to MEA we have found out. Let's talk about ME at C. Potential energy mgh, that is 0, height is 0, plus half m Vc square. Vc, suppose over here that is Vc, and we are asked what is the value of Vc. So let's see it. So it is mg2r, it is 2 mgr plus half m rg is equal to half m Vc square. So this is 2 to 4, 5 mgr by 2 is equal to half m Vc square. 2 and 2 cancel. So Vc comes out to be root 5 gr. So this is the minimum velocity at the bottommost position, so that it is able to navigate the circle, complete circle. When root 5 gr, the velocity will be given over here, then as it rises, the velocity will reduce, the speed will reduce, and when it comes over here, it will be root rg only. If you wish to find what should be speed at d so that it is able to navigate the circle, then we can find once again, we can put it as equal to MED. So anything we can do, that is ME at A is equal to ME at D. Same way, potential over here, mgh plus half m v square rg is equal to over here potential energy mg hs. This is the reference level. Midway we cannot change the reference level. Reference level is this. So if we are taken for this potential from this reference level, then if we have to find the potential energy of this point, we cannot change the reference level. From here to here it is r, so from here to here is also r. mgr plus half m v d square. Obviously this is the minimum velocity at the point D, which is required so that this is able to, the stone is able to navigate the circle. So it is once again mg2r plus half mgr is equal to mgr plus half m vd square. So this is 5 mgr by 2. This comes over here, minus mgr is equal to half m vd square. So this is 3 by 2 mgr is equal to half m vd square. M and m get cancelled, 2 and 2 get cancelled, and vd comes out to be root 3 gr. So this is the minimum velocity at the horizontal level it should be having, so that this stone is just able to navigate the vertical circle of radius r.